Assalamualaikum warahmatullahi wabarakatuh. My name is MOHD ZAMRI. So our group will give a summary of chapter 2, which is Newtonian mechanics, rectilinear motion of particle. So this is a chapter outline for this chapter, starting with 2.1, Newton's law of motion, 2.2, rectilinear motion, 2.3, force that depend on position, 2.4, velocity that depend on force. So I will start with 2.1, Newton's law of motion, historical introduction. So classical mechanics is built upon the core ideas of Sir Isaac Newton's law of motion. The Newton's law was created by Sir Isaac Newton. Sir Isaac Newton established three basic principles of motion in his 1687 Principia, which would permanently alter how people saw the universe. So the three principles are: first, law of inertia, that states everybody continues to in its state of rest or of uniform motion in a straight line, unless it is compelled to change that state by force impressed upon it. Second is law of acceleration. So the change of motion is proportional to the motive force impressed and is made in the direction of the line in which that force is impressed. So third is rule of action and reaction. So to every action, there is always imposed an equal reaction, or the mutual action of two bodies upon each other are always equal and directed to contrary parts. So next we move to the Newton's first law, which is initial reference system. So the first law describes a common property of matter, namely inertia. So it states an object at rest will remain at rest, and an object in motion will remain in motion with a constant velocity unless acted upon by a net personal force. So choosing a frame of reference or a set of coordinates in configuration space that can be used in determine location, velocity, and acceleration of the particle at any given point in time is necessary for a mathematical description of a particle motion. So frame of reference in which Newton's first law of motion is valid is called an initial frame of reference. So a frame that is not accelerating is known as an initial reference frame. It might be at rest or moving at a constant speed. So it is crucial to remember that not every frame of reference is initial. Frames that are speeding are known as not initial frames, and object in them will feel imaginary or pseudo force. So the initial reference system is crucial because it gives the rule of motion a context that makes sense and ensure predictable behavior. Next, we move to the mass and force, which is a Newton's second law and third law. So imagine someone pushing the two masses together, compressing the spring, and then suddenly releasing them so that they fly apart, attaining speeds V1 and V2. So we define the ratio of the two masses to be M2 over M1 equal to V2 over V1. So if we let M1 be the standard of mass, then all other masses can be operationally defined in the above way relative to the standard. So which is the delta M1 V1 equal to negative delta M2 V2. So the initial velocity of each mass are zero, and the final velocities V1 and V2 are in opposite directions. So the equation becomes differentiate of M1 V1 equal to differentiate of M2 negative M2 V2. So this operational definition of mass is consistent with Newton's second law and third law of motion. Thus, the second law can be written as M equal to K d mv over dt, where K is a constant of proportionality. Considering the mass to be constant, independent of velocity, we can write F equal to K d mv over dt equal to ma, where A is the resultant acceleration of a mass, M subjected to a force F. Thus, we finally express Newton's second law in the form of F equal to ma. So the force F on the left side of equation is the net force acting upon the mass. That is the vector sum of all the individual forces acting upon M. So the equation equivalent to F1 equal to negative F2, which is the Newton's third law. Next, we move to the linear momentum. So basically, momentum is V equal to mv. So linear momentum proves to be such a useful notion that is given its own symbol. So Newton's second law may be written as F equal to dp over dt. We can see from here is equation equation here is which describe the behavior of two mutually interacting masses is equivalent to d over dt m1 mv1 equal to negative dt d over dt m to v2. So we substitute by using the formula of momentum p equal to mv. So we will get d over dt equal to p1 plus p2 equal to 0, where p1 plus p2 is constant. So Newton's third law implies that the total momentum of two mutually interacting bodies is a constant. So the law of linear momentum conservation is one of the most fundamental law of physics and is valid even in a situation in which Newtonian mechanics fail. So we move to the next part, which is motion of a particle. So here we see here is the equation of Newton's second law, which is F equal to Fa. So we can get the motion of particle equation by emphasize this point by writing F as F net, the vector sum of all the forces acting on the particle. So I will share here is the usual problem of dynamics. So given a knowledge of the force acting on a particle of system particle, so calculate the acceleration of the particle. Knowing the acceleration, calculate the velocity and position as function of time. So this process involves solving the second order differential equation of motion. So a complete solution requires a knowledge of the initial condition of the problem, such as the values of the position and velocity of the particle at time t equal to 0. So the initial condition plus the dynamics detected by the differential equation of motion of Newton's second law completely determine the subsequent motion of the particle. And that's all for me. Thank you.
Now, 2.2, which is rectilinear motion, uniform acceleration under a constant force. Rectilinear motion is referred to the motion of an object along a straight line. In other words, the object is moved only in one direction, or either horizontally or vertically, without deviating from the straight path. This type of motion is characterized by the changes in the object position along the chosen line over time. The general equation for the rectilinear motion is the fx in bracket x dot t equal to mx double dot. The x is a position, which is the location of the object along the chosen straight line. It is usually measured from a reference frame point or origin. And s dot equal to velocity, which are the rate of changes of the position with respect to time, which is dx over dt, and it is a vector quantity and has both magnitude and direction. And t is, which is the time. When the acceleration is constant, x double dot is which are equal to dv over dt and f over m, and is constant, which are the acceleration is constant. So in the rectilinear motion is simplified model that is used often in the physics study basic principle of the motion before moving on the more complex scenario involving multiple dimension or curved pipe. It is fundamental concept kinematic equation, which is branch of the physics that deal with the motion of object without considering the force causing of the motion. Next, from the first equation that we got, which is fx s dot t equal to mx double dot, we can get the solution is readily obtained by the integration with respect to time. We integrate the equation with respect to time, and we got these two equations, which are x dot equal to v equal to at plus v naught, and x equal to 1 over 2 at square plus v naught t plus x naught. V naught is the position of the velocity, and x naught is the position at the t equal to 0. By eliminating the t, the time, which is t, between the equation, we can get this last equation, which is 2a in bracket x minus x naught equal to v square minus v naught square. That's all for me. Thank you.
Assalamualaikum. My name is Muhammad FARIS bin Muhammad SAFIEN, and today I'm gonna talk about the force that depend on position. Potential energy functions are commonly used to describe forces that are position dependent. So the amount of energy that an object has stored depending on where it is in a force field is known as its potential energy. Within this field, the potential energy changes as an object moves. Understanding the motion and interactions of objects within a physical system requires an understanding of these fundamental concepts. So these are the characteristics of kinetic and potential energy. The number one is kinetic energy is always non-negative and is a scalar quantity. Number two, the kinetic energy of an object increases with mass or with motion speed. Number three is kinetic energy is transferred between the objects during collisions, impacting their afterwards motion. And number four, the final choice of reference point affects the sign of potential energy, which is a scalar quantity. Next is free fall. So what is actually free fall? Free fall refers to the motion of an object falling under the influence of gravity without any other forces acting on it, except for the gravitational force. So in a vacuum where air resistance is negligible, all objects near the surface of the Earth experience the same acceleration due to gravity, which is approximately 9.8 ms². So there are some aspects about free fall. Number one is gravity. Number two, uniform acceleration. Number three, independence of mass. Number four, equations of motion. Number five, vertical motion. Then we move to the free fall example. So why is it called constant acceleration? It is because free fall is actually related to gravitational acceleration, which is g, that valued 9.81 mg². Then we use kinematic equation, which is total initial energy equal to the total final energy. S is upward. The gravitational force, which is Fg equal negative mgh, is negative because the gravity is downward. Next, the potential energy is negative dv over dx equal negative mg, and v equal mgs plus. Kinetic energy plus potential energy is 1 over 2 mv² plus mgh equal E, or T plus V equal E. The V naught or U, which is the initial speed, is 0, and also the equation is upward. The maximum height or the potential energy height is V equal to 0, K equal to 0, and the potential energy is max, which H equal to X max or V naught over 2G. And the result is K of equal max, which means that 1 over 2 mv square.
Hi, Assalamualaikum. So for my part, I will talk about the velocity that depend on force, which is fluid resistance and terminal velocity. So let's start with their definition. Firstly, the fluid resistance. In fluid dynamics, fluid is a type of friction which refers to opposite force relative to the motion of any object travel with respect to a surrounding fluid. Next is terminal velocity, the highest velocity attainable by an object as it falls through air. It occurs once the sum of the drag force and buoyancy equals the downward force of gravity acting on the object. Since the net force on the object is zero, the object has zero acceleration. So next, force in terms of function of V can be described in two forms, which is F0 plus SV equal to m dv over dt. Second is F0 plus Fp equal to mv dv over dx. The approximate measurement for fluid resistance is as follows, which is C1 and C2 is constant value of shape and size of the object. Next is the value of the constant that depend on shape of sphere on air is as follows, which is C1 is 1.55 multiplied by 10 to the power of negative 4t for linear term, and for C2, which is 0.22 d to the power of 2 for quadratic term. So next is quadratic term to linear term ratio as below. So what is horizontal motion with linear resistance? Horizontal motion with linear resistance involves the motion of an object moving horizontally under the influence of a resistive force that is directly proportional to its velocity. This results in a decrease in velocity over time, and the relationship is mathematically expressed by Newton's second law and a solution that exhibits exponential decay of velocity. So let's move to the first example. Suppose a block is projected with initial velocity v0 on a smooth horizontal surface and that there is a resistance such that the linear term dominates. Then in the direction of motion, f0 equal to 0 in equation 2.4.1 and 2.4.2 and f v equal to negative c1 v. The differential equation of motion is then negative c1v equal to m dv over dt, which give viewpoint integrating as below. So how to solve this? We can easily solve for v as a function of t by multiplying by negative c1 over m and taking the exponential of the both sides. The result is v equal to v naught exponential to the power of negative c1 t over m. Thus, the velocity decreases exponentially with time. Second integration gives as below. So lastly, showing that the block approach limiting position given by x limit equal to m v naught per c1. So let's move to the example 2. If the parameters are such that the quadratic term dominates, then for positive v, we can write negative c2 v to the power of 2 equal to m dv over dt, which gives as below. So for the solution, solving for v, we get v equal to v naught over 1 plus kt, where k equal to c2 v naught over m. Second integration gives us the position as a function of time as below. So that's all from us. Thank you.